introduction. So maybe I can just move around here and be also on the webcam here. So hello everyone again. We'll be luckily having Miko today from Bose Research, Miko Kegler. He's an audio machine learning scientist at Bose Research, and he is mostly working with like low latency, lightweight, and like on-device systems for audio and speech processing ML. And I know Miko does a lot of other stuff and works on different technologies as well. So, prior to Bose, he got his PhD from Imperial College of London and working on neuroscience, I guess. Yes, and working on like perception of speech and some like other audio systems, like cognition of those speech signals, etc. And previously, he has interned at like Amazon, Logitech, like those like different companies. And I know Miko is working on a lot of stuff these days. So I think we are very lucky to have him today. And let's give the stage to Miko.
Okay, perfect. Yeah, thanks a lot for having me and for the very warm welcoming. Since we already burned 6 minutes, I'm not gonna spend much time on this slide. Here's the title that you were looking at for a while now. And before I start, I want to make a few like acknowledgements and disclaimers. So basically, most of the work I will be presenting, it's not only my work. It's basically a work of a great team of people consisting of research interns, people from Bose Corporation, and many more collaborators. And on top of that, I would like to express that I come here as a scientist to talk to scientists, and the opinions that I express are my own and they're not the views of Bose Corporation as a whole. All right, so what I will be talking about. So I will start with like the kind of general franchise overview of what is Hear What You Want, what is our mission, what do we want to accomplish, and so on and so forth. Then I'm going to go how we try to actually make it happen through tiny ML for like causal low latency speech processing tasks. Then I will switch the gears a little bit to talk about text-to-audio generation, the project that we were working on last year, and how to actually improve its efficiency and efficacy. And finally, I will do my best to leave plenty of time for Q&A and questions. All right, so let's start with the kind of general overview of what is Hear What You Want. And like you probably know Bose for their noise cancellation. There are headlines like that where someone tried the ANC earbuds and almost got hit by a bus, right? I mean, so we can confidently say that we are pretty good at noise cancellation. We are trying to solve this problem and we are doing pretty well. So what we want to actually tackle is to create this active noise cancellation 2.0 in a way, right? The noise cancellation that will be adaptive and selective depending on the circumstances, user intention, basically give you some sort of immersive ability to interact with the world, not block everything out, and that's it. And basically, the general idea is we want to allow you to hear what you want whenever you want. So basically, to kind of put some meat on those bones. What we are doing now is kind of blocking all unwanted sounds. You stroll through the busy streets of London, you can cancel out the city sounds to hear your music clearly or podcast or whatever you are into. But then if there is a cyclist on the pavement, right, you want to hear their bell ringing and to jump off or politely ask them to use the cycling lane that's nearby. And basically, the similar picture can be painted in the pubs, right? You're in a kind of really busy place. There is the football playing, Euro Cup, and so on, and you're trying to have a conversation with someone, just understand them. And basically, what we want to allow you to kind of selectively pass through the voices that you want to hear. For example, people sitting in front of you, and so on. And this problem is particularly relevant for hearing impaired people for whom this feature is a must, actually, if you are using hearing aids. And Bose is partnering with some of the hearing aid companies to make those experiences happen and improve the quality of life of hearing aid users. But then in the same situation, right, when you have an urgent phone call and you need to take it, you don't have time to move out, right? What we want to do is completely opposite. You want to cancel pretty much all of the sounds so that your own voice can be clearly audible to the person on the other side. And in principle, basically, we want to create this kind of, the opportunity to customize your ambience. And here is like a little demo in VR in which a virtual person is pretty quiet. This person on the beach, there are children yelling, some engine running in the back and so on. And what we want to do is just click the switch and hear only the waves crashing and so on. If you can't hear it, believe me, it's there. Yeah, basically it's kind of like the ideation, like what we want to accomplish here. Okay. So basically, you might think, okay, it's just a bunch of source separation and kind of unmixing the world and remixing it in a lot of clever ways, right? And to accomplish that, what we need to do is to actually have something that runs in a very low latency setting, right? Otherwise, the delay will be kind of audible, and you won't have kind of a nice experience with that, right? So a big bulk of our work is kind of around crafting those low latency algorithms that can be deployed directly on the device, not a smartphone or a cloud, which would incur pretty long delay depending on the circumstance. And as you probably know, the current generation of wearable audio platforms have pretty limited compute that I'm gonna highlight in the next slides. So basically, in this talk, I'm gonna kind of try to show you how to train your tiny ML model and basically how to make those tiny ML models perform well. So let's embark on this journey. And one more thing, I will try to share the slides later. If you are looking for kind of more in-depth, full academic course, there is a great resource at MIT. There is a course all about tiny ML. So make sure to check it out if you are interested. So yeah, so the first principle, right, in this whole tiny ML game, tiny audio ML game is to kind of know your limits, right? Understand your platform, how much compute you can have, what are your restrictions, and so on. And for that, I'm going to use the tiny LSTM's paper that my colleagues published at Interspeech in 2020, I think, where they run a case study of what are the common limitations for platforms like hearing aids and so on, where you have to take in mind the compute complexity, model size, working memory, data type, and the general perceptual quality to run on this little chip. And to give you some perspective, right, this little chip that's kind of not that uncommon in small wearable devices is about 20 times less powerful. That's what's running on your current gen iPhone, right? So basically, to kind of give you the scale of what we really need to do to make those little algorithms happen. So basically, now that we know our limitations and where we can position ourselves, usually the right way to go is to already start small, right? Don't try to have a very large model and kind of try to slice it in different ways. Just start with something small, performant, meeting all your requirements, right? So basically, in the tiny LSTM paper, the architecture is truly simplistic. It's literally 2 LSTM layers, processing like the power spectrogram, followed by 2 fully connected layers, and that generates the time frequency masks that is supposed to be applied to the input time frequency spectrogram, and that's how you kind of suppress noise. You filter out speech from noise, right? And basically, like one big savings here is that we are using kind of magnitude only processing, right? There is no phase, there is no complex parts, which save you a lot of compute, like understandably for some performance sacrifice, right? But usually, this trade-off is something we can accept. And another two parts that you can notice is that we are using mal transform to focus on the kind of speech-specific spectrum, right, to not have the linearly spaced frequency bins, which also kind of reduces the input size, and then the associated sizes are kind of smaller, right? And compression is very common kind of bio-inspired preprocessing. So in general, like psychoacoustics and DSP and standard classic DSP are your friends in this battle. Use them as much as you can to craft those hybrid systems. Okay, so now that we have our simple model, right, you might have noticed that one of the requirements that's really common on embedded devices is to quantize your model to run with like integers, not floating point data types. And the way to do it, one way is very simple. Basically, you take your trained model and you just squash the weights. You convert them literally to like integers. You encode them with like Mantissa exponent or something like that. But as you might have guessed, right, the model is not used to this kind of lack of precision, and then we lose the performance. So that's not ideal. So what we can do instead is to do the quantization of our training, right? Where basically, as you train your model, you simulate like what would happen if this was quantized, right? While all the training is running in the full precision. So basically, for each like activations, input, output, biases, pretty much everything, you can apply basically the quantization operation to kind of to fake it in a way. And you can have like the different dynamic ranges. Basically, the model can pretty much automatically set things in the right places for it, which is pretty neat. And in the next paper that I'm going to talk about from NeurIPS 2021, I think, or 2022, my colleagues proposed this kind of quantization EQ. That's even simpler method, where basically you limit the dynamic ranges of all the parts of the model to be fixed, right? And then you can say, okay, but it's probably not optimal. Some layers need more dynamic range, some models need less dynamic range. And what they found out is if you simply put like a very simple EQ layer at the input and apply those strict constraints, the model works just fine, right? So basically, the EQ layer is compensating for those limitations in dynamic range. And I'm going to show you a bunch of numbers. I'm going to focus on basically the stuff highlighted in color, so you can ignore the rest. Basically, the main metric for most of the evaluations for the source separation will be the signal to distortion ratio, which basically means the higher number, the better your separation performance, right? And here we have three models: the baseline model that is like full precision without any EQs and so on. And then you can see the model that has the EQ applied. And you can see that we get a little bit of performance boost, which is quite cool to see. That basically we apply this quantization and we add this EQ, and we get some free performance, which is pretty neat. And finally, when we train the model with this QEQ way, we quantize it after the training. You can notice that the performance like barely changes, right? It's pretty much all the same. But what you can notice is that the size of the resulting model is effectively 4 times smaller, because we go from 32 bits precision to 8 bits precision, which is pretty good to see. Okay, so now that we have like figured out the base model, the quantization, we can actually deploy it in the hardware if we meet other requirements, right? What we may want to do is to kind of reduce the size further, right? To save some compute, save battery life. This is all stuff that we want to do. And the core idea in pruning is very simple. Just remove selectively weights and try to reduce the number of parameters, which gives you like less compute. And you can do it in 2 ways. You can do it offline. So you take your trained model and you derive some heuristic. For example, look at the magnitude of the weights, right? And remove n% of the smallest weights, and then hope for the best. which immediately doesn't really work that well, right? But you can fine-tune your model after this pruning and repeat the process a few times. However, the other thing you can do is you do the online pruning, right? So basically, on top of your kind of task objective that you want to solve, you can add the additional loss term that corresponds to the penalty for having a lot of weights, right? And basically, this way, the model can optimize, how to strike the best performance with the smallest number of weights, right? And obviously, you can fiddle with the hyperparameters to, choose how aggressive it will be, and so on. And another distinction that we can do in pruning is to go unstructured or structured, right? In the unstructured way, it's like complete free-for-all. You can remove any sort of individual weight from anywhere. And in structured pruning, we try to impose some sort of structure. For example, remove one filter from a set of convolutions, remove like a block of weights that are neighboring together, and we generally try to add some structure to this pruning operation. Well, why does it matter? I will talk about in a second. And here is like a visualization of how this online pruning can look like. So here is like an LSTM layer from the tiny LSTM that I was talking about. And on the right-hand side, you can see what happens when we remove like blocks of weights in this online pruning procedure. You can see that the network effectively evolves, reducing number of active weights, which are denoted in white, and becomes more and more dark, right? As the pruning progresses, we are increasing the number of weights we want to remove. And in this kind of structured pruning, my colleagues in the paper basically considered kind of weight pruning, in which you pluck individual weights, the block pruning, in which you kind of you take, I think, sets of 4 neighboring weights because of the hardware they were using, was sort of optimal, or remove the entire units of the neural network, right? Which gives you like this kind of those crossing patterns, And basically, like, why do we even consider those 3 ways to go? And the answer is that, if you have the weight pruned model, right, the resulting model that you have is very sparse, right? If you go like really hard, you have like very kind of individual weights scattered around somewhere, right? So you cannot really do the clean and nice matrix multiplication and so on. You need special support from the hardware that is not very common in most cases. If you have some sort of piece of hardware that does it well, I want to talk to you. And basically, you can see like the graph, right? Like basically the sparsity percentage on the x-axis and the actual speed up of the inference on the y-axis. And this is data aggregated from the two papers that I quote here. And this is supposed to give you like the kind of the general overview. How does it look like, right? So in blue, we have the weight sparsity, right? The individual plucking of the weights. You can see that the speed up is actually negative for the small degrees because basically we have to take a lot of weights that are already pretty sparse, find the corresponding activations, multiply them, and so on. However, for the block and unit sparsity, the situation looks much nicer because, if you have the unit sparsity is the simplest case, right? You basically still have your full dense matrices, you just remove a few rows or columns and so on. And for the block, it's kind of in between, right? If you have like the structured sets of 4, right, you can basically realign them together, and then it should still work. Right. So basically, how does this impact the performance? And this is like the kind of semi-comprehensive look at signal to distortion ratio. So first thing you can notice are the dashed lines where we do actually offline pruning. This is, I think, without any further fine-tuning. And you can see that if you train your model and then just try to prune it in the offline way, you quickly lose performance, and this is like not the best way to go. However, in the top 3 lines in the solid, you can see that you have the blue line, which is the weight pruning, which gives you the best performance, like the least drop off in performance as you go, because you can kind of craft your own optimal solution by plucking individual weights. Then you have the green one, which is the unit pruning, removing all the units, which is pretty coarse, and that causes the biggest drop in performance. And the kind of block, removing the sets of neighboring weights, is kind of the best trade-off you can get in this situation. So in general, as most things in life, there is like no free lunch, and you always you always need to make some sacrifice. All right. So basically, this is like a look on a bit more detailed performance, but I think I'm going to go through it fast because you can see that as we progress, we reduce the size of the model, a number of parameters. Our signal to distortion ratio drops a little bit depending on the setting, and as we go further, the further size decreases, and then we make some larger sacrifices, right? And then finally, in the largest sparsity, we compressed our model by effectively 40 times from 4 megabytes to like 90 kilobytes, and we can get a speed up to 7 while sacrificing only like 0.5, 0.6 signal to distortion ratio, which is in general a pretty good deal. But you might ask, is pruning the only way to go, right? Can I just have to go through all those steps and take away my weights and do all those kind of all this magic? And the answer is no. There is also like a pretty classic technique at this point, which is knowledge distillation, right? Which basically is quite the opposite to the pruning, right? Instead of having a larger model and trying to cut away from it to make it smaller, instead you start with an already small model, and you have some sort of larger model, for example, 10 times larger, 20 times larger, 30 times larger, that's pre-trained. And that can actually influence the smaller model as it trains, like try to transfer some of the knowledge to either speed up training or make it more effective, right? And the most typical formulation I can think of in knowledge distillation is simply having your standard loss denoted with L and some knowledge distillation loss, right? And the knowledge distillation can be as simple as comparing the outputs of the models, or in case of classification tasks, you can compare like the logits of the final layer. So when we started researching this project, we noticed that the methods has been pretty popular all across the field of ML, but for some reason not so much in kind of source separation tasks. So we wanted to see like what's going on there. And yeah, this is what brings me to the next paper, the two-step knowledge distillation for tiny speech enhancement that we worked on. It's actually work of Ryan, who might be somewhere online in the chat. If you are here, say hi, Ryan, afterwards. And yeah, and the question we are trying to answer, like how we can improve the performance of those, causal, low latency, tiny ML models for speech extraction in this case, using knowledge distillation. So a few semi-boring details before I move on to discuss more results. So the task is, again, noise suppression, right? You have a noisy speech and you want to have clean speech, right? For applications like hearing aids, communication in noisy bars, and augmented hearing in general. And the task and the data set that we are using is fairly kind of golden standard in this field, Microsoft deep noise suppression data set, which is like a lot of data of speech, a lot of data of noise, and you can kind of mix and match them to create your training evaluation sets and so on. The model we are using here is slightly changed for a reason that we just wanted to try something else than LSTMs. And this is like a pretty simple kind of unit model that Microsoft developed as a part of the challenge, I think, if I remember correctly, which is basically a few kind of encoder layers that are stacked together. Then there is like the RNN bottleneck, and then you have a few decoder layers, right? And as in the classic unit, you have some connections connecting the encoder and decoder to facilitate the flow of information. And for the kind of supervised loss, the non-knowledge distillation loss, we use pretty standard, very sensitive spectrum approximation, which for the sake of simplicity, we can think about it as complex L2 pretty much. Between the model output and the target, right? And you want to minimize it to make sure that you predict clean speech from the noisy inputs. However, we believe, we didn't test it, but but in general, the methods developed in this study can be applied to other tasks, models, and so on, right? It's not really about the particular setup we are using as our test bench. It's kind of more about the method in general. So keep that in mind. So in this case, we basically approach the problem pretty simply, with teacher and student having like exactly the same topology in terms of number of blocks, number of layers, sizes of kernels, and so on, with one difference that the teacher is just much larger, having many more units in each block. So if you compare the parameter numbers in teacher and student, you can see that our student is only like 3% of the teacher, going from 2 million to roughly 60,000, right? And the number of operations per inference is also dropping to about 6% of the teacher, right? So we try to kind of go deep already. we are not kind of doing it in a small increments. We want to have a big gap. Yeah, and again, and the loss that we are using here is the same as I explained before, where the KD loss is simply comparing the outputs of the teacher and the students, and hope to propagate this knowledge through the student. And then we have the kind of the backbone loss, which is the supervised loss, right? You basically have a task loss component and the knowledge distillation component. And drum roll, it didn't work. So basically, in this paper, I will show you a lot of those studies, right? When in kind of top two rows, you will see the teacher and student performance on their own, like as they were trained independently, right? And then in the bottom, I will be showing you a bunch of results of different distillations, right? So in here, this is like kind of what we call out distillation based on the model outputs. And for the metrics, yeah, this is a sad phase because it didn't work. You can see that the SDR that we already know and like from the previous slides is pretty much not changing with respect to the student trained alone. So we are like not very happy about it. We are like, what can we do now? So one of our hypotheses was that distilling the outputs of the model might not be the way to go, right? Can we leverage the fact that our student and teacher have like very similar structure and basically kind of try to transplant the latent patterns, right, in the model? So basically do the knowledge distillation in the latent space of the model. But there is obviously a problem, right? We can't compare them directly because teacher is much larger than the student. So what we can do here? So what we actually ended up doing is to try to compute like the self-similarity across the batch items in each batch. So basically, you can think about it as I have activation A for item A, activation B for item B, and kind of encode it in some way that I'm going to explain right now. So in this left panel, you can see the kind of the problem that we are trying to do. You have the student model with some blocks S0, S1, S2. You have the teacher model with blocks T0, T1, T2. And then what you want to do is to compare the S1 and S0 and T0 and kind of match them, right? Make sure that the activation patterns are kind of similar for those models to transfer the knowledge, right? But again, the problem is we can't really do that. In the paper, we also tried actually distilling the knowledge across the layers to basically model how the information flows, but I'm going to skip it from this talk because it wasn't as effective as we suspected, but we still included it in the paper because we found the method is quite cool. Okay, so basically how we can find this G transform, or how can we transform our activations to make sure they fit. And the solution is pretty simple, right? We have the activation pattern that has like batch, channel, and let's say time and frequency dimension, right? And the problem that we have is that channel number is different, right? So what we can do is we can simply transform our set of activations to have like the batch dimension and everything else like connected all together. And then we have the B by B matrix if we matrix transpose those two reshaped matrices, right? It's great. We can just compare them, no problem. The only problem is that it doesn't really do much. So we went to another method that was actually proposed in one of the papers before. We can leverage the fact that our model is causal, right? That means that the time dimension for each kind of latent activation is the same because you need to process kind of stuff frame by frame, right? So what you can do is you can compare those self-similarities for each individual frame instead of just kind of aggregating across time, which makes you lose like granularity of those representations and so on. And that's basically in line with the paper that we took it from. It improved the performance a little bit, which we were glad to see. Just for completeness, we try to leverage the fact that our kind of decimation of the frequency dimension of the input is similar and did the same thing across frequency, which we didn't really hope it's going to work. It actually improved stuff a little bit, not too good. But what ended up working the best for us is actually, doing the self-similarity for each individual latent time frequency bin, right? Which, if you think about it, gives you like the most granularity to kind of compute the losses and get the best performance in a way. So in general, we were glad to see that that our initial hypothesis seemed to work out, improve the metrics the most, but we still wanted more, right? Those improvements are good. They can compensate some of the performance we can lose via pruning or something like that, but they are not like really that impactful. So then we started to question, like, is it a good way to go to optimize the knowledge distillation loss and this anchor supervised loss together, right? Like, what if one can overpower the other, and this is like this, fight for power, in general. And what we proposed is to split this process in a kind of two steps, right? Instead of doing everything from scratch in kind of one go, you can, for example, try to schedule your gamma hyperparameter, right? So for example, for the one-step knowledge distillation that I explained before, we have the KD and the PSA losses like optimized jointly. You have the gamma of half, and each of them is contributing the same, right? And you can take the same number of epochs, and you can split it in two parts, right? For example, in the first part, you only want to do the knowledge distillation. You don't care about your test performance. You literally want to copy your teacher. And then you start doing the kind of the weighted knowledge distillation, right? And in the third, even more extreme pattern, right? You basically first do only knowledge distillation, and then you say, screw the teacher, I'm just going on my own. And you do the supervised loss. Which basically you can think about like going to school, right? You go to school, you copy your teachers, you pass your exams, and then you go to the real world and you learn what's out there. So yeah, so basically these results are kind of the same results I showed you before. This is the first row in the bottom part is the kind of one-step knowledge distillation that we have. This is just for visual reference. And here we have the results for splitting them in kind of two steps, right? So in the first row, you can see the pre-training with the latent knowledge distillation that I introduced. And in the top row, you can see the only supervised loss, so basically the third panel. And in the second, you can see this kind of 50-50 loss. And in principle, both of them worked. Like one of them was marginally better than the other. But in general, it seems that this kind of KD only pre-training conditioning is doing something right. But you may say, right? I mean, okay, but doesn't the model unlearn anything when you remove the teacher, right? And we actually try to test it by looking at the similarity of the activation patterns using the method called CKA, which you can think about, more similarity, more similar. So here's the student trained independently of the teacher, right? They are kind of trained completely separately. And you can see that, there is not a lot of pattern, the similarities are not particularly high, and so on. And here is the student following the latent KD pre-training, right? Like as expected, you can see the diagonal like lighting up like crazy, because this is literally what we are doing here, which is good to see that our method is working. Basically, the activations of the student are similar to the activations of the teacher, right? And now, drum roll, does it forget everything? And the answer is no. Actually, if you kind of train with the supervised loss following this pre-training, you can see that the similarity between teacher and student is actually larger than than for the two of them trained independently. And the way we interpret it is that the model starts from a good place, right? It learns what the teacher can accomplish, right? They basically copy the same activations to the same inputs. But then, it literally cannot achieve the same performance, or it would be very hard. So it has to learn its own way. That's why it kind of the similarity drops, because it starts from a good place, and then it simply learns its own method. All right. So like as a final couple results, right? Like one thing, we are still not quite happy about our results, and then we realized that the test set we are using is having pretty high SNRs, right? Basically from 0 to 20 dB with an average of about 10, right? Which gives you some perspective. It's not that difficult. And what we know is that very small models are actually not doing bad in those situations. Where they really struggle is kind of lower SNRs and just more difficult cases. So what we try to do is we remixed our test data set to have different SNRs. Basically, we took the samples of speech and noise from this test set and we shuffled them in a different ways. And what we found, actually, if you compare, for example, SDR in those tables between student and our proposed knowledge distillation method, is that we get the biggest performance boost for the lowest SNR, which is pretty neat for us, because this is where we need the biggest performance boost. And basically, this kind of tends to roll off as we go to the higher SNR, right? Which basically more or less aligns with what we thought that that the most impactful this method will be for the most difficult cases. And yeah, and to be kind of full and complete, what we did was we tried to experiment with different sizes of the student model, right, to see how small we can go. And we noticed a pretty similar trend that if you start with if you go for the smallest student with only 30,000 parameters, you get like the most relative improvement, right? And the larger your student becomes, the less it can benefit from this knowledge distillation. So yeah, just to reiterate, our method seems to give the most improvement for the lowest SNRs and for the smallest student model, which is exactly when we need it, which is pretty good. Okay, so basically like a 30-second recap of what we are talking about, right? So if you want to train those tiny ML models, you need to know your limits, understand your platform, where are you going to deploy it, what are the limits, and then start small, right? And start to design your model in a kind of clever way, right? Try to offload as much computation to stuff like classic DSP, or build like a hybrid DSP ML model, right? Because ML is powerful, but it tends to be big as well if you want to solve every problem and so on. And then if you have your kind of small, tiny model, right, you can further optimize its size, complexity, and so on through the methods like quantization, pruning, and knowledge distillation. And that's more or less it for this part. I will take questions at the end if that's fine. And I will go to the second section that I have some content for. So this is all about improving text-to-audio generation that you must know quite a lot about being in the Center for Digital Music. This is a pretty hot topic now. And you might ask ourselves, like, why do we care about it, right? The current generative AI is not directly applicable for inference on the small wearable platforms and so on. But what we still can do is use it for creating other experiences, right? I mean, we can potentially make you hear what you want, even if it's not in your surrounding, right? We can basically synthesize some soundscapes that are nice, that are fitting your current mood, and simply send it to your earbuds via Bluetooth, as we do it on the phone. And this is like one of the many other applications. Some of the other ones might be, for example, generating some synthetic data for training model that's already going on in the field pretty much. And as a kind of sandbox for experimentation in this field, we use DK's task 7, in which the objective was to build the system to generate 7 distinct sound classes based on the text input, right? And the winners of this year's DK's challenge, or last year, I guess, depending how do we count it, is the kind of task fine-tuned text-to-audio audio LDM with post-filtering of generated samples. Don't worry if you didn't understand the thing. I'm gonna introduce it step by step. So the first question is what actually is audio LDM, right? Which maybe some of you know, maybe not. So I will just go through the whole thing. So audio LDM is this kind of scary-looking diagram on the right? And the main ingredients of the audio LDM, where LDM stands for latent diffusion model, is the pre-trained CLAP model, which is the pre-trained text-audio multimodal representation that basically tries to kind of bring audio and text in the similar space. The hi-fi gun, which is the pretty classic neural vocoder for generating the samples, and variational autoencoder that can help us encode stuff. And how does it work? So basically, in this diagram, you can see two types of lines: the dashed line where we talk about inference, and the black line where we talk about training or fine-tuning. So if you take a look at the training path, right? What we do is we have like a piece of text. We generate the text embedding from the pre-trained CLAP model. Then we run the diffusion process that I'm not going to go to in details, but you probably know the pictures of the dogs getting more blurry and then undoing the whole thing. And then what we want to compare it with this diffusion process loss, we want to compare it with the VAE encoded sound, right? So basically, your latent diffusion generates kind of the sound that's text conditioned and is matching what the audio is described with the text that you provided in the other branch, right? And that's more or less it in super high level terms without getting into too many details. And for the inference, you can follow the dashed arrows, right? In which we take a pretty simpler route, right? Where you take the text embedding from the CLAP, you process it through the diffusion model, and then you take the output of the diffusion model, run through the VAE decoder, and then vocode it with the hi-fi gun, because basically the input to the hi-fi gun at this point is a kind of null spectrogram, and then you can get your audio sample at the very end. So that's more or less it. And let's focus on what the winning system was doing in the DK's challenge, right? And first thing that they were doing is actually very simple method. They added like a tuning layer, just simply fully connected, if I remember correctly. Layer that was kind of readjusting the text embedding, right? Because they were starting from a larger pre-trained model that was general text to audio, and they wanted to specialize it for this DK's task. So they added this little adapter layer that was really simple and really effective, and we all like those methods. And the second thing that they did was actually added this score filter at the end, right? Which basically worked in a way that you generate samples. You compare the generated samples CLAP embedding with the text embedding, right? And basically, if they are close enough, you say this sample is good. If it's not close enough, you generate another sample, right? And basically, this is pretty impressive and also pretty hacky because you can generate it over and over and over again until you kind of satisfy this distance, right? And your samples should sound good at this point. And what we didn't quite like about the method is that it's really wasteful, right? If we want to run this diffusion model to generate the data of like good quality, we have to run it like many times, right? And we have to derive like heuristics how to set those filter thresholds and stuff like that. So first idea that we have is, okay, can we just use this post filtering and train the model, try to condition it so that does the post filtering like internally and so on. But unfortunately, that didn't work because back propagating through this whole bunch of steps, most of which are pre-trained and they're not being used in the actual training, is just not feasible. It's blew up our GPUs. I think we got it working for like batch size of 1 in one setting, but it was just not very sustainable, let's say. So what we try to do is introduced in this paper latent club for better Foley sound synthesis. And our idea here was, can we not post filter the output, but can we do some sort of post filtering in the latent space, right? Instead of having it in the kind of waveform domain, can we do this in the, for example, output of the latent diffusion domain, right? Because we don't need to go to the end of the chain and then, it's just much simpler, right? But the question is, how to compare samples in this latent space. There are many places you can tap in and so on. And one of the ideas that we had was to add this kind of another branch to the club model, which we call latent club, which basically take the output of the latent diffusion model, which should be the VAE encoded audio clip, right? And then we compare it with this audio clip, right? So if you think about it, right, the output of the latent diffusion in the classic setting depends only on text, right? And we want to compare it with audio. But now we want to compare it with this kind of latent representation of the audio, which is a little bit different in this case. Okay, so basically this is how this latent club loss works, right? Basically, you have your audio signal, right? And this is how we pre-train it, where you have one kind of STFT embedding with mel frequencies that is VAE encoded, and then you process this latent through this latent representation through the latent club, and the second thing is coming from the audio club branch, right? So basically, you can think that we added like a third head to the club model. And yeah, and basically we do it mostly because to kind of make sure that the latent output is similar to the latent club output, right? And basically this is what effectively they were doing in the post-filtering step, but at the output, right? So this is pretty much the way to do it in the latent space, or at least this is what we could think of, right? For reference, you can see how it works for the standard club, right? And the one difference is that the club is contrastive. This is what the C stands for, and we actually use MSE loss that we found works better in this case, which sort of makes sense because we want to make it like as similar as possible. Right. So basically, like does it work? Does it actually do anything? And for evaluation of the system, we use the Frechet audio distance, which is the metric representing the quality of the generated audio, where lower score means better quality, although quality is debatable, let's say. And this is probably a good crowd to discuss it with. Okay, so the first thing that we tried is just the pre-trained audio LDM model, right? There is no fine-tuning for this task, and we got some sort of score, right? In the first row, I show the real audio results, and these scores are computed by basically processing the audio through the whole chain without the latent diffusion, right? So this is how much performance you lose just by doing the VAE decoder and hi-fi gun. Or I think it's only hi-fi gun in this case. Okay, let's go to the next model. So basically, this is the audio LDM with this tuning layer that I mentioned, which drops your score quite nicely if you look at the average on the right-hand side. And then you have the audio LDM with our latent loss that we introduced, which drops the performance quite even more, right? One thing to note is that this setup doesn't include the tuning layer, which we add here that gives us the best performance, right? So what we did was kind of put all those ideas together, and well, as expected, we got our metrics to the best place, and it's pretty consistently best for, like, I guess most of the classes, or at least the differences are not that big. And then we kind of tried to do the post filtering in those different settings in the bottom part of the table, right? So basically, those are the same models as before, but with some post filtering that we added, right? You can say, okay, why the scores are not 0? You can post filter until you reach the happy place. And the answer is that we want to kind of keep it pretty realistic. We did a comprehensive post filtering that we ran for a while, according to the recipe that the winners of DKs did, and those are the score that we obtained. So basically, if you compare this kind of our best model from the top part, which is LDM plus tuning layer plus latent clap, right? It's actually only marginally worse than just the LDM plus latent plus post filter, right? Which is really good, which is exactly what we wanted to see, that our latent clap loss seems to be working as a post filter that's internally influencing the model, right? It doesn't require any post filtering, right? So in other words, you can think about the top part of the table as kind of zero-shot generation, and bottom part of the table as, you know, this post filtering and selecting the right clips. Yeah, but I kind of alluded to, you know, the quality being not the FAD being not the best quality estimator. So what we did was we ran a simple listening test where we generated a bunch of samples with a few different models, and we asked 40 people to rate them, right, according to the perceived audio quality and the class relevance, right? So basically, is this sound like, you know, dog barking, keyboard, or something like that? And one shocking thing that we found was actually listeners preferred synthetic audio to the ground truth in terms of both audio quality and class relevance. And we are like, oh my God, are we stealing Foley artist jobs? The artist was no. The ground truth samples in this case were actually quite noisy. Right? I'm gonna try to play some examples to visualize what I mean. But if you check out the paper, there's a link to the whole, like, website of samples, so you can check it out for yourselves. Right. So this should be dogs barking. This is ground truth, plenty of dogs. This is our baseline model, which is the LDM plus tuning layer. Pretty good, a bit repetitive, maybe like not the highest fidelity. And this is our model that we proposed. It sounds very good. There's a bit more bark to the bark, I think. And here's an example of, you know, of how the ground truth samples can sound. So this is supposed to be, I think, keyboard sound. You can hear this really loud, like, HVAC noise, you know, this air conditioning. And this is why we think the reason the ground truth were rated lower, because they just have a lot of, like, background noise. There are some people talking in some clips and so on. And yeah, just for completeness, here are the two clips from the two systems. This is the baseline, sound a bit hollow. I'm not a big mechanical keyboard guy, so I leave the judgment to you if it sounds good. And this is the proposed model. This is a bit more action, I guess. All right. And that's it. Thank you very much. I miraculously fit in the time limit with 6 minutes to spare. And yeah, and one thing to mention, you know, we are obviously like a company that works on new products and so on, and we are always looking for talented people to join us, be it at the intern position or full-time position. So here's the QR code if you are by any chance looking for opportunities. Thanks a lot. And yeah, I'm happy to take questions, and yeah, I got no plans for the rest of the day, so I'll hang around if you want to engage in a longer discussion. Yeah.
I have two small questions.
Yeah.
Thank you so much. I think it was a great talk. It was so clear. I'm mostly curious about the tiny ML work and the knowledge distillation part.
Yeah.
So regarding that gamma hyperparameter, probably tuning the weight of those different contributions, I'm curious, have you tried some periodic schedulers as we benefited from that idea in like KL divergences in the context of PEs, or perhaps some learnable parameters for that gamma so that all of those different weights scale individually? Or classify free guidance literature like taking that gamma very extreme, we don't have any theoretical basis, but maybe something surprising people see.
So I will start by like learnable hyperparameter, right? For me, it's kind of a chicken and egg problem because it's in the loss part. So the model can just learn to not do KD by assigning the hyperparameter to be 0 or 1 depending on your formulation, right? So basically, this idea I'm not a particular fan of because it allows model to cheat, find loopholes and stuff like that, right? At least that's my perspective. For the scheduling, yeah, this is basically what we are trying initially to kind of do some sort of smooth exponent and something kind of less transient. But yeah, after a few tries, we got a bit frustrated. We just decided to split it in two parts, right? So instead of going for the big screening of what's the optimal way of transitioning, we just went for do A, do B. That's it, right? So yeah, there's definitely some more room for exploration, but there's literally like countless possibilities that we could explore, which we probably should, because it might be that this is not the optimal solution. And yeah, and for the schedulers, I think you mentioned that kind of like switching this in a clever way, right? I mean, I think that can be done in a similar way, right? Like in general, as I was presenting this work at ICASP, it was highlighted to me that this is non-orthodox KD, because usually the steps are flipped, right? You first train your model, and then you fine-tune it with the knowledge distillation. So this is like kind of the other way to go, which we found quite interesting. I think internally we ran a few experiments like that, but they didn't really differ much from just doing the kind of joint optimization and so on. So it might be because of of the small models, because of our task setup, because of many factors that going the other way is actually better. Yeah.
Thank you. And knowing that explanation things didn't work out and we tried them and so on.
Yeah, I mean, it's not that it didn't work out. It's just I think we got too lazy to try them for long enough. Yeah, I'm generally, like try to deal with as little hyperparameters as possible. Let the optimizer do the job.
Second short question would be about the tiny ML like model pruning and stuff in that context. So I think with those weights or blocks or chunks, whatever, practically we are just regularizing that training scheme from a theoretical perspective. But from the ML perspective, people use some other regularizers to achieve some sparsity in the networks. So do you know, is there a connection between what we mechanically do in the model, like pruning or taking out some weights, or adding some external regularizers to the model so that we can achieve sparsity? Do they correspond to some theoretical understanding in the scheme, or I'm just curious about connection.
Yeah, I think they are incredibly related, right? If we go back to the slide with the pruning.
One nice figure about the matrices.
Yeah, which one was it? Oh boy, it was a while ago. Latent KD pruning. Yeah, actually, if you look closely, we are adding like the L2 norm to the weights, right? So we try to do them both at once, right? Because what you want to prevent, right, is kind of this overcompensation in a way, right? Which then would kind of interfere potentially with your quantization, right? Yeah, I think they are both related, right? And I think there can be some link made with this quantization EQ, right, where you kind of limit those when you apply those hard constraints for the dynamic range, right? which also make the network, potentially, get stuck in a fewer wild places, and so on. In terms of like the at least weight values and so on. So this is, I guess, in my understanding, some sort of regularization as well by applying those constraints and compensating with the input EQ. Yeah.
Thanks. I missed the answer. Thank you.
Yeah, no, don't worry. It was a lot in a short time.
Thank you.
Yes, please.
I think you add the latent loss
Mm-hmm.
for the audio idea.
Yep.
And you provide results for the zero code and the results for the fine-tuning. I wonder why the loss can contribute to the performance without fine-tuning.
Sorry, no. What I meant to say, this is all fine-tuning. This is no model trained from scratch, right? So basically, in each case, we take the pre-trained model and we just fine-tune it on a task, like the winners of the DK's task 6, right?
For the second row and
yes.
Third. I mean, for the third row and the fourth row.
Yeah.
The third row is LDM plus latent, and next is LDM plus tuning plus latent. So what is the tuning layer?
Tuning layer is this this tuning layer right here.
Oh.
Yeah. So basically, this is like this kind of simple, simple adapter that we can add to improve the performance, right? Yeah. So basically, like the general audio LDM was trained on general text-to-audio, right? In this case, for the DK's challenge, we just want to have like 7 sounds that are generated well and consistent. So this is like one way to improve the fine-tuning of the model. All right. Any more questions? Yeah.
If you can say this, what development platform they use for the IML hardware?
Yeah. So it's fairly known that Bose has strong connections with Qualcomm. So basically, we are we are not manufacturing our own chips, and we are using like Qualcomm chips in most of our products. That's pretty much the most I can say. Yeah. Yeah. I think Otherwise, if my boss is listening, he's gonna.
In practice,
yeah.
When do you move in your research cycle? When do you move to testing on hardware? I guess you need avoid it as long as possible.
Yeah. So basically, to testing on hardware, there are like two parts, I guess. Like one part is to see whether we achieve generalization and so on, and just kind of setting up like the demo in a way. And this doesn't necessarily have to be all like quantized and fancy schmancy and so on. We can use some sort of like other prototyping equipment that we have to just quickly run some models, and this is what we try to do as soon as possible, just to see if we achieve satisfactory performance and so on. And then testing on hardware is as you can expect, it takes time. There's like some sort of there's the entire embedded team that need to step in and kind of wire it into other like audio processing chains and stuff like that. So it definitely takes the longest, but whenever we show signs of something working, we try to pull the trigger and get it tested as soon as possible. Yeah, there is of course like performance benchmarking in terms of like if our estimated compute matches what we see in hardware, because it's no matter how good your simulator is, there must be something that's a bit off, and so on and so forth. But yeah, we are definitely kind of action biased in this case. Just try to test those experiences better, because demo speaks for itself. No matter how many tables with results you show. Yeah. Hopefully coming to you soon in those products. All right. If that's it, thank you so much for your attention. It was an absolute pleasure and honor to present here. My first time at Queen's Mary for 8 years in London, so it's about time.
Thank you so much.
Thanks a lot, guys.
Thank you.